In 2021, while driving across the US, I found myself snowbound in Nashville, Tennessee, in a small hotel room for 3 days, my trusty dog, Oakley, by my side. Ironically, we took the southern route across the country to minimize weather delays and instead drove headlong into a cold front, which was part of the infamous Texas freeze. The entire state was caught off guard and unprepared. Millions shivered without power and water, isolated and afraid. While the rest of the world was watching these events unfold, I was on a video call with Dr. Ray Schmidt, an oceanographer of 40 years from the Woods Hole Oceanographic Institute, his twin sons, and his PhD student, who were describing their latest science project, a weather forecasting technology that predicted the Texas freeze weeks before local forecasters did. They were sharing it with me and asking if I could help them bring it to the world. 250 people died in that storm. And in the weeks that followed, I kept asking myself, how might things have been different with just an extra week of notice and preparation? And not just for the Texas freeze, but the many other extreme weather events that are occurring more often these days. When moments matter, it can mean the difference between life and death. Our understanding of weather is changing for two reasons: ocean data and artificial intelligence. The weather forecasts that we rely on every day are based on fundamental equations that simulate the atmosphere. The inputs to these equations are things like air temperature, pressure, and density. These simulations work great for the coming hours and days out to about a week. Beyond that, they're unreliable because small errors compound when stepping these equations forward in time. You experience this whenever your weather app leads you astray, or the local weather forecaster gets it wrong, yet again. When forecasting weather further than a week out, the atmosphere becomes less and less predictive over time. The land and the ocean become more predictive. So instead of feeding variables like air temperature into equations, it's more effective to focus on things like soil moisture and ocean temperature. The relationship between atmosphere, land, and ocean, however, is very complex and difficult to replicate with physics equations. That's where artificial intelligence is bridging the gap and learning new connections that can help us reliably forecast further into the future and lead us to a world where hopefully we can avoid situations like what happened in Texas. Communities can be prepared and lives can be saved. I'm an entrepreneur, not a scientist, but I've had the privilege to lead incredibly talented oceanographers, hydrologists, and meteorologists for years. Our current challenge is predicting weather from 2 weeks to 1 year in advance. It's called subseasonal to seasonal forecasting. Subseasonal means weeks ahead, seasonal means months ahead. It's also known as S2S for short. I want to share with you why S2S matters, what we are doing, and how we are doing it. To understand why S2S matters, let's start with energy. Homeowners, hospitals, and businesses increasingly rely on stable electricity from wind farms, solar farms, and hydropower. Yet the fuel sources, wind, sunshine, and rain, are variable and uncertain. Most large electricity producers have on-staff meteorologists who monitor weather in the coming hours and days, but they're flying blind beyond a week or two. In the Texas freeze, gas and coal power plants froze. Natural gas supply and delivery equipment froze. And wind turbines froze. Even though there were strong signals in the subseasonal to seasonal forecast weeks before, which could have prompted preventative action. The result? Skyrocketing energy prices and millions left without power and water. In fact, the only people who benefited during this tragedy were energy traders who use S2S forecasts and were able to predict many of these things before others. Energy markets work best when everyone has predictability. It lowers the costs. S2S forecasts are an important piece of that puzzle. So why are S2S forecasts important to our food? Many farms in Kenya grow sorghum, which is an important food crop in East Africa. The majority of sorghum is grown on small farms of several acres by smallholder farmers. They're the lifeblood of Africa's food system. Droughts, diseases, and pests can wreak havoc on their crops and lead to widespread food shortages and hunger. Every day, these farmers are making decisions to try to navigate around these risks and maximize their yield, like deciding what seed varieties to plant, when to plant them, how much fertilizer to apply, when to apply it, when to harvest. The list goes on. All of these decisions are based on weather in the coming weeks and months. And most of these farmers don't use S2S forecasts in their decisions. Instead, they rely on historical weather patterns from past growing seasons. But those weather patterns are changing. How about our water? In South Africa, there's a reservoir called Theewaterskloof. Millions of people in Cape Town depend on it for their drinking water. In 2018, after a period of prolonged drought, the city narrowly avoided a day zero catastrophe when all of Cape Town's water would have been shut off. Large water districts have hydrometeorologists on staff who help inform decisions about how much water to let out of the dam or when to alert downstream districts about potential water shortages so that they can take precautionary measures. Yet most of these decisions rely on historical weather patterns and not S2S forecasts. What's common here are people making decisions that depend on weather beyond the typical 2-week window. We just saw that most of these decision makers assume that future weather will look like the past. They may plot the last 30 years on a graph and say, on average, the first week of June over the last 30 years is 78 degrees Fahrenheit. But our temperatures are warming, so averaging the last 10 years is probably more reflective of what's normal today. Temperature swings are also increasing, which is why distributions are widening, which means more uncertainty, more volatility. The rates of these changes depends on location, time of year, and whether we're talking about temperature, precipitation, or wind. If this is starting to sound confusing, you're not alone. The most experienced decision makers in the world are also scratching their heads, which is why we need to move away from assuming that future weather will simply look like the past and move toward better subseasonal to seasonal forecasts. Over the past 20 years, government weather agencies have been squeezing more juice out of those short-term atmospheric models by stretching them to forecast weeks and months further. The smartest meteorologists use these models, but with a grain of salt, because they perform just marginally better than using historical averages. That said, the combination of ocean data, land data, and artificial intelligence is creating a step change at this timescale versus anything that we've seen. Our team has demonstrated that this methodology outperforms historical averages consistently by more than 30% in terms of accuracy and confidence. And here's why that matters. It's creating trust with decision makers. But even with that trust, these are hard decisions to make. For example, if you knew that weeks before the Texas freeze, there'd be a 65% chance of severe weather and extreme low temperatures that could cripple infrastructure, that still means there's a 35% chance of normal temperatures. And while 65-35 is much better odds than flipping a fair coin, that still leaves a lot of uncertainty. What do decision makers do in that situation? Do they quickly go out and spend tens of millions of dollars winterizing equipment? Who actually makes that decision? When do they make it, and what if they get it wrong? Our ability to forecast further in advance is improving. So too must our ability to make better decisions. So how are we improving our sub-seasonal to seasonal forecasts? Well, it starts with the data, and the first place we look are the oceans. Remember Dr. Ray Schmidt? Back in the 90s, he and other oceanographers had a vision of thousands of sensors like this sinking and rising around the oceans, capturing temperature and salinity or saltiness data. Thanks to the dedication and collaboration of scientists around the world, today that vision is a reality. Each one of these dots is a sensor, and there are almost 4,000 of them capturing this data and sending it to satellites once every couple of weeks. And we can find patterns in that data. This is sea surface temperature data. Red is warmer than average, blue is cooler. Most of you are aware of El Nino, which is when this patch of ocean off the coast of South America becomes warmer than average once every few years. This often results in predictable precipitation and temperature patterns around the globe, including some of the places that we looked at earlier. This is sea surface salinity data. Red is saltier than average, blue is fresher. Who remembers their 5th grade science class where water evaporates from one place and precipitates somewhere else, the water cycle? Well, this partially explains why an increase in salinity off the US Atlantic coast in the springtime is related to Midwestern rain in the summer. Artificial intelligence is great at finding connections like this across space and time, and not just for sea surface temperature and salinity, but dozens of other variables. This data-driven approach is where our field is moving. To do this well requires teamwork between scientists who understand the physical interactions and individuals skilled at implementing the latest AI techniques. While most of the innovation around weather forecasting to date has been led by government agencies, the private sector is pushing the pace of this next wave of innovation. And because of all the benefits of better S2S forecasts, we're seeing more collaboration between public and private sector than we ever have before, which is uncovering even more uses for the combination of ocean data and artificial intelligence, like improved hurricane forecasts to keep us out of harm's way, better sea level rise projections to ensure that our coastlines are prepared, and identifying those places in the ocean where we can sequester carbon, which is one of the many tools needed in our attempt to pull it out of the atmosphere. When I think back to being snowbound outside of Texas in a hotel room with Oakley, I realized that that storm marked the beginning of a journey for me. I see the world differently now. I see the ocean differently. It's no longer just a vast expanse of blue water. It's a treasure trove of data and information. And it's teaching us if we listen. Thank you.